Now that we have both our catchments covering our entire site area as well as a representative flow path for every catchment, we can actually use the analysis tools in Civil 3D and find our values that we need. So the first thing we need to do is just a little bit more prep work. I guess you don't technically need to do this, but I would wager it'd be very helpful for you to label all of your catchments. Your catchments, again, are just every area where the water will flow to one point. And we need to do some math with this using the rational method. So it will help you keep track of what numbers go with what area if you label everything. You can label these by number, 1, 2, 3, 4, 5, 6. You can do it by direction, northeast, southeast. You could say sidewalk, lower, hill. It's up to you to choose how you name these. But give all of your catchments a name and do that in Civil 3D, and then we'll jump over to Excel and do a little bit there too. So, for example, I might call this one northeast catchment. This one might be northwest. I know my text is small right now. I will make it all and then scale it all up at the same time. So just do the same thing that I'm doing here. That's all of my names down, so I'll select one, right-click it and select similar, and then scroll down into my text properties and change that height up to, for example, 6. Much more visible now. So now that we have these named, we need to do a similar thing inside of Excel. So Civil 3D will give us numbers that we need for each catchment, but it won't actually do all of the math we need it to do. So I'm going to go over into my files and into my analysis folder that we have. I already have the sidewalk elevation file in here. You might as well. And in here, I will create one, and I will call this Stormwater Analysis. So what we're going to be doing in this file is creating two tables, one for our existing site and one for our proposed site. And we will calculate the runoff from each of the catchment areas that we have and sum them together for each site. And then that's our comparison. Our proposed site should be lower than our existing site. So here I will write, for example, existing site, and then I can do proposed site over here. Site. I'll make this look nice later. So here I'll do catchment name. And what do we need here? We need Q equals C, I, and A. So I'll do the coefficient here. I can do intensity here. And then area here. And then my flow rate as Q. You can make these columns however you like, but this is what you need. And you will be turning this in. So for my catchments, I will simply kind of copy over the names. I think I have northeast, northwest, west, southwest, south, and southeast. So these are my catchments, and that is the first part of our table filled in, the first column. Now let's move on to the second column. So we need coefficients. And if you remember about these runoff coefficients, the runoff coefficients are a property of your surface characteristics and what materials you have. So a really porous surface, for example, a pond or like a sand sort of soil, something that's really loose that lets in a lot of water, would have a really low coefficient, where something that is very impermeable, would have a high runoff coefficient. So example might be asphalt or concrete will have a really high coefficient. And that coefficient correlates to the amount of water that turns into runoff versus groundwater. So the higher coefficient means more of that water will be runoff. A lower coefficient means more of that will be groundwater. Modern water treatment practices, stormwater practices, aim for more groundwater treatment than stormwater treatment. Every addition you have to stormwater and to runoff means you need to have bigger pipes, a better system, maybe more treatment for water. Some cities, or honestly a lot of places, have combined stormwater and sewage water treatment. So it means you're treating all of this stormwater, which is technically clean as it's falling, and you're using a lot of resources and a lot of energy to do that. So we want to minimize our runoff. Runoff also contributes to erosion. So minimize runoff, maximize groundwater infiltration instead. So we are going to get our coefficients for these. Sorry, that was a long-winded explanation. We will get these from a VDOT table. This is linked in your assignment document. It is just a giant amount of information, all having to do with hydrology, and this is from VDOT standards. So what you're looking for in this is the table E in the appendix. So as you scroll all the way down, table E-1, rational method runoff coefficients. So I believe that is page 59 here. Yeah, 59. So this is the table we'll be using. Under the table, there are a couple of comments that you should use to determine your runoff coefficients as well. But notice that all of these are ranges, and there is some sort of engineering judgment that you need to use. So going back to our Civil 3D, you can sort of take a look at your catchment areas and your runoff coefficients and figure out which use case best matches the catchment. So for example, the lawn description here of 0.25 to 0.35 would probably work really well for my field. But I would most likely need to use the steep grass for the hill part. Now, my big catchment, northwest catchment here, has some area that I could consider to be a lawn and some area that I could consider to be a hill. It also has some impermeable surface with the sidewalk. So how do I know what runoff coefficient to pick? Well, you basically need to take a weighted average. So the weighted average is based on the coefficient you pick and the area you have for each of your coefficients. So I could use the polyline tool, for example, and I'm going to turn on my object snapping here and say I want this much area to be the field or the lawn. I think all of this is flat enough here that it could pretty much be the lawn. And notice I'm not being exact, but that is okay here. You should probably be a little bit more precise than I am being right now. But when I select that polyline, I get an area inside of Civil 3D. So this is square foot area. You might remember that we need to use acres for the rational method for the unit to work out like really easily. But we're taking a weighted average here, so this doesn't actually matter that's in the square feet. It just matters how much square feet this is relative to my other areas. So I might go back to my Excel table and below this do a separate calculation, or I can do this on a separate sheet if I want to. So for the northwest catchment, for example, I might have 3 different coefficients. I might have steep grass, and I might pick that to be, it's a pretty steep hill that we saw from the grade, so I might go closer to the higher value here, so maybe 0.65. And I'm going to use the lawn value as well. Again, not totally flat, so I'm going to do 0.3. And then lastly, we have that paved surface. So paved areas are 0.9. And it might actually be better to break this up a little bit more. So I might do it as like this. So this is my coefficients, and this is my northwest catchment. It's up to you. You can do this all in a calculator if you want to. Just doing it in Excel so you can see it. And I said my lawn area is 29,780 feet. Now I can do the same thing for my other two areas. One nice thing is you already have the area of your whole catchment because we extracted this. So I know, oh, actually, since it's a 3D polyline, it doesn't show it. But if you convert it to a 2D polyline, then it will. So I can make another polyline, and I can just delete these all at the end of making these, and say all of this is my hill area. And looking at this one, it looks like we have about 18,250. And then do the same thing for my paved area. I will get rid of those lines. Oh wait, they're not existing. And then here, I'll do the same thing. And again, I'm not being super exact. You should probably be a little bit more precise than I am being. And this area that we're dealing with here is 3,325. So now that I have these values, I can do a weighted sum to figure out what my total coefficient is. So that would look like multiplying these values together, and then adding, and then multiplying, adding, multiplying, and then I will divide this entire thing by our total area. So now you can see that I should take my coefficient value to be about 0.46, and this is my northwest catchment, so I will put that as 0.46. So you need to go through and do this for all of your catchments. So the fewer catchments you have, the easier this will be. But just go through, use the table, use a weighted average. You don't need to be exact, but you should be able to support your claims. So supporting your claims could look like having math like this. Supporting your claim could also look like having written justification. But whenever you turn this in, we need to be able to see why you picked those coefficients. So please show that. Do that for all of your catchments, and then we'll be back with the next step. Now that I've finished making my coefficients, we can go back and create our catchments. So I just want to point out that I added one more column, time of concentration here. We'll need that to determine the intensity. So make sure you make that column as well. I will be very surprised if the time of concentration is anything other than 5 minutes for every single one of these, but we have to do our diligence and check anyways. Again, make sure you're showing all of your work. I have my numbers already from doing the whole project multiple times, but make sure you show yours. So going back into Civil 3D, we can actually make our catchments that Civil 3D recognizes. So we'll go over to the Analyze tab, and under ground data, there is the catchment here. So we will first create a catchment group. This works pretty much like the grading groups and everything. It's just a way of grouping them all together, hence catchment group. I'll call this existing stormwater. Apply and OK. Now we're going to use the create catchment from object. And here is where we can start selecting our boundaries. So I'll start with this polyline, and it's asking me now to select a polyline on the uphill end to use as a flow path. So that's the one representative flow path that we've kept. So I'll select that, and now the creation box shows up. This is part of the reason why we named our catchment. Name it the same thing, Northeast Catchment. Make sure it's on your site. We are not dealing with pipes here, but know that Civil 3D has the power to model all of the culverts and pipes and everything that you might find underneath the ground. From here, we can go to the catchment properties, we'll keep it as the standard style. Here, make sure you let it show your name, area, and properties. And for the flow segment, you can set this to none. We don't need to know any information about our actual line that we made. Here it's asking you to make a runoff coefficient, so get that from the table you just made. This is my northeast catchment, so I have a value of 0.032. And you can erase existing entities that will replace this polyline in our catchment boundary with the one that Still 3D makes. It's mostly up to you. I think it's fine for it to be erased and replaced. Then we can go over to the flow path tab. Here, just make sure that we have TR55 as the calculation type. It should be the only one you can see. And for the flow path slope, select from surface. And here, select existing ground. Now I can click OK, and it runs, and you can see it makes our catchment. It also keeps me in the catchment creation, so I can go right into making the next one, but I'm going to exit out of here really quickly just to talk over some of these features. So the purple boundary is our catchment area. The yellow point is where our water line or our flow path starts, and the blue circle is where it ends, with the light blue line being the actual flow path that is representative. This is the important part, though. Here we can get the area of our catchment in acres, which is what we need, and we can get the time of concentration, which is also what we need. You need to go through and do this for all of your catchments and transfer this information over to your Excel file. Now, just remember that for time of concentrations, the chart that we'll be using doesn't go less than 5 minutes. So any value you have lower than 5 minutes, we just assume that time of concentration is 5 minutes. So if you have any values less than 5, all of your values most likely will be less than 5. Make sure you round up. Make all of your catchments, as I will do here in a second, transfer that information over, and you will need to submit a plan sheet showing your stormwater analysis with all of these catchments created. All right, so I finished up here. If you have anything that shows up as like question mark, question mark, question mark, that's okay. Just assume 5 minutes. They're all going to be 5 minutes. So just do that. You can move these around, which is nice. So again, you will need to submit a screenshot, or sorry, not a screenshot, a plan sheet of this. And now I have all of my values here, except for intensity, which we will do in a second. The last thing I can do is sum my areas to get the total site area of 2.05 acres. If I am able to select my surface, which might be a little bit difficult, but if I select my surface, we should have a total surface area similar to that. So when we do our proposed site, since our boundaries haven't changed, we should also have an area of 2.05 acres. And that's a good check to make sure that we got all of the areas that we need. To get our intensities, we are going to use the NOAA website to gather this information. So you should have hopefully seen this by now in class or on your homeworks, but if not, here you go. This is also linked in the deliverables. I'm sure it's also linked in the slides or the homework as well. And here we can get hydrological data from a bunch of NOAA sensors and stations all over the entire country. So we can find the sensor that's closest to us and use that to get our table values of precipitation estimates. So I am going to start by typing in or selecting a station. So I might see if I can use a zip code, 22903. That works. And it zooms us in here. And now it should be using the closest station to that area. But if I really wanted to, I can also go here and actually select my station physically. So Charlottesville 1, for example, is there. Mount Jefferson, or Martha Jefferson. And then Charlottesville 2. You can see where that is. So we can use that. And now looking down at our values, we can get our 5-minute values, because that is all of our times. Our concentrations are 5 minutes. And here we are going to be looking at a 25-year storm. So if you look at the average recurrence interval for 25 and 5, this is our value. There is a confidence interval technically associated with this, but we are just going to use one value for this. Now the funny thing here is all of our time of concentrations are the same, which means this value is the same. And so I will take this number and it's just going to be our intensity for all of them. So now I can make this look a little bit prettier. You know, you guys can do all of this, I trust. And I can calculate the flow rates. So remember, it's Q equals C times I times A. I can drag this down and then do a sum. And this is our total value, right? So we're looking at 0.62. I think this is cubic feet per second, if I remember my rational method correctly. And what we're looking for now is that when we do our proposed site development and we do the analysis there, that this number is lower. That's one of the requirements of the project. So that's all of the existing site analysis. In the next video, we'll go over BMPs and scorecard additions. And the last video after that, we'll be doing this same process again for the proposed site. You already know how to do it. You do the exact same thing here, but I will sort of walk through the whole thing again for the proposed site and just speed it up so you guys can see what that looks like.